a problem which is related to the concept of equilibrium. So you have a cylinder, okay? So this is your cylinder actually. If you just see, this actually is a cylinder, okay? And this cylinder has two spheres in it, and the diameter of the cylinder is available to us. So this is the diameter of the cylinder. These two spheres, have some weight which is acting down, okay? W, and this also has a W. And these two spheres are not moving, okay? So these two spheres are not moving. They're held stationary. And the question is, the dimension of the two spheres is given to you, that the spheres are identical, and they have, this as 5 centimeter and 5 centimeter as the radius. So these represents the centers, the C1, and this is the C2, the center of the two spheres. Now, if you look into this, this, arrangement is in equilibrium, which means the net forces on the sphere number 1, which is shown to be, in orange, and the other one is also 0. So the net forces on sphere number 1 is 0, and the net forces on the second sphere is also 0. Okay? The way to, look at these numericals is, essentially what you have to do is you have to draw the free body diagram, which is where the main thought process is. But before you do that, in terms of free body diagram, you must understand that, this line, is inclined at some angle. And since these two spheres are touching each other like this, okay, they're touching each other, and the centers can be connected to each other like this. This is your C1 as shown above, and this is your C2. So the normal reaction, because the two surfaces are in contact, will exist here. So you will have a pair of normal reaction between the two spheres, which can be shown like this. So this sphere exerts a normal reaction like this, and this sphere exerts a normal reaction in the opposite direction. Okay. So between these two spheres, you have a normal reaction. And the direction, because the normal reaction is a vector. So whatever normal reaction is being exerted on this body or on this body, the angle, the direction of normal reaction should be known. If you look into this diagram very carefully, this is known to be, 10 centimeter, because this is the radius and this is also the radius. So this becomes 10 centimeters. And if you know this is 10 centimeters, and if you look into, the fact that this overall, this thing is 16 centimeter, this is 5, and this is another 5. So what you left, if you subtract this radius and this radius, from 16 centimeter, so 16 minus 5 and 16 minus 5, you're left with this particular length, right? So this particular length is 16 minus 5 is equal to 6 centimeters, okay? This is known to be 6 centimeters. This is the hypotenuse. If I label this triangle, I call it A, and I call it B, and I call this as C. AC is now 10 centimeters, okay? And this particular thing you have calculated with the help of cylinder. Cylinder has no mass, nothing, just offers some walls around it. So this particular, the dimension is 6 centimeter. This is 10 centimeter now because it's sum of two radius. So you actually have a triangle, which is 10 centimeter, and then you have this as 6 centimeters. So you can always find this angle, and this is the direction of your normal reaction, right? So the normal reactions, are acting in this direction, right? Now, if you look into this, so let's draw the free body diagram of sphere number 1. So if I were to draw a body diagram of sphere number 1, and let me just rub this off so that we can understand, it'll tell you exactly how do you apply the condition of equilibrium. So I'm just drawing the free body diagram of this sphere. Let's say this is your sphere, okay? Now it is touching the surface down below, okay? And I'll just bring the attention to the down below, the surface. Let me just adjust. All right, now I hope you can see it in a better manner than, let me just adjust it a bit so that you can, see this. All right. So if we were to, draw the free body diagram. So this is the place where it is being touched. So you have a normal reaction available here. Okay. There is a normal reaction which is coming from this side also, which is this. And then the body has some weight, right? So the body also has a weight which is W. And then it touches the other sphere, right? So you also have a normal reaction which is coming from the other sphere, which is like this. And we know this angle, by the way, from this triangle, which we calculated using some, subtraction of the radius. We were able to find this hypotenuse and we were able to find this. So you know this angle. You know the direction of normal reaction. You know a normal reaction is coming from the cylinder, which is at this point, you have a normal reaction, which I'm representing with N1. And then, the ground is also offering, it is touching the ground also. The ground is offering some normal reaction here. You can call it N2. And then you have a contact force here also, which is coming from the sphere above, which is pushing it down. But the sphere is at rest, which means all the vertical forces. So if this is your normal reaction 3, and you know the angle theta from this trigonometry, what you can do is you can write the sigma of y, all the vertical forces is equal to 0. And then you can write the sigma of horizontal forces to be 0. Obviously, you will need to do a resolution of N3. The N3 resolution, is essentially this, right? So this is N3 sine theta, and this is N3 cos theta, right? And then this is a horizontal force. This is also a horizontal force. So this normal reaction is equal to this one, N3 cos theta, and N3 sine theta, which is acting downwards along with the weight, plus this is equal to the, the normal reaction coming from the ground. So you can write all your equations in X and Y. Similarly, go to the second sphere. Draw the free body diagram of the second sphere. The second sphere has a weight. It has a normal reaction, which is coming from, the surface, which is, I'll just show you in a minute how it comes, right? So this is your normal reaction coming from the wall of the cylinder. You also have a normal reaction, coming from the second sphere, which is this, right? This is a second normal reaction. Again, do resolution of this normal reaction, which is this and this. So you know that this component is equal to this component, and this component, which is the vertical component of coming from the second sphere, is equal to the weight, the W, okay, of the second sphere. Put the equations as sigma Fy and sigma Fx twice, once for this and second for this, and you should be able to calculate the different contact forces or the normal reaction which is acting between these two. So the trick in these questions is essentially, you have to use some trigonometry using radius and the dimensions of the cylinder. So it is not apparent when you look into the nature of the problem. Where is the cylinder located? Cylinder is the enclosure in which these two spheres are residing, and the dimensions of cylinder are given. And then, of course, the standard equation of equilibrium is to be applied in X and Y direction to calculate the various reactions which are being, acted upon these two spheres. So I hope this made sense to you. These questions, are, aimed at checking your concept of equilibrium, one of the most important topics, you can expect an entrance examination. So thank you very much for watching my video, and please keep an eye on more videos to come. Thank you very much.